So, simple machines, simple machines. Let's do just a quick, it's been a long break, so let's do a quick little review of work and energy stuff, and then we'll jump into simple machines. So, quick review from last, week and a half or so prior to break. So, work we define as force times displacement, right? If we want to have a little more precise version of that, we multiply force times displacement times the cosine of the angle between the two. Right. Okay. Kinetic energy, 1/2 mv squared. Work energy theorem tells us that the net work is equal to the change in kinetic energy. Right. So the net work. Now, what does that mean? Let's focus on that for a second. Net work you can think of in two ways. Equally good. Doesn't matter. You could either think of it as the net force times the displacement of an object, which is probably the most natural way to think about it. Or you could just add up. That sigma just means sum, right? We just add up all of the work due to each individual force, right? I could calculate the work due to every force and then just add those numbers up as scalars. They're not even vectors then, right? Just add up those numbers and that's going to give us the net work. Okay? So I guess what then? So that takes us all the way down. And then last thing I want to include, make sure we include, is this little number down here. Okay, this is the other version of the work energy theorem that I don't think even shows up in the online textbook, but it's one I want you to be familiar with. This really cool theorem. So if we define mechanical energy as being kinetic and potential, right? The sum of kinetic and potential. So 1/2 mv squared plus mgh, where you have to just determine where you're measuring the height relative to and then just stick with it, be consistent, right? Then any change in the total mechanical energy has to be due to work being done by non-conservative forces, right? The sum of those two, which gives us mechanical energy, if we, for example, lose some mechanical energy, then some work must have been done by a non-conservative force. 99 times out of 100, what's that non-conservative force?
Gravity.
No, that's conservative.
Friction.
Friction, yeah. Friction would have robbed the system of some energy, right? Okay, make sense? You've done some problems like that, with a bike coasting up the hill, so you've had a little bit of practice with that. Hopefully you're done or getting done with those. Moving on though, let's talk about a couple more things. We mentioned this right before the break, and a lot of people were gone, just in case not everybody was here when we talked about this. Power is what we define as the rate at which work is done, right? So it's work divided by time. So the amount of work done divided by the time taken to do that work. So we talked about buying trucks, right? Good Eastern Oregon topic, buying trucks. When you talk about horsepower, you're talking about a machine's ability to do lots of work in a short amount of time, right? And that's for sports cars, that would mean you're able to accelerate really fast. Okay, you're able to you convert that into speed is what you're looking for, right? You're able to change your speed rapidly. What do you think the horsepower is of that car?
380.
467. That's a big time engine. I don't even know. I just pulled it. I know that's the horsepower rating that went with that car though. What do you think the horsepower rating is for that massive tractor?
180.
60. Okay. So power is not necessarily. Some people confuse what power is doing. Like when you're working with a tractor, what are you trying to do? Well, you're just trying to provide lots of force, but not necessarily at very high speed, right? And so you may not actually be doing that much work, but you're able to provide pulling a plow through the ground or something. The car simply can't do that. It can't provide enough force to push that plow through the ground, but that guy can, right? So it's not going very fast, but it can provide lots and lots of force, all right? So once again, power is the rate at which work is done. Okay, let's talk simple machines then. So now we've got an idea, had some practice talking about work and energy, and we'll continue with that as we move on. But let's apply this whole concept to some specific things now. Let's apply this to a series of what we call simple machines, and they are very simple. So without looking at the bottom here, what are these things? What's that?
A lever.
Lever. Yeah, so one category of simple machines would be levers. Okay, and what first thing we'll talk about today are levers. What's that?
Pulley.
Pulley. Okay. Pulley system. Yeah, it's sometimes called a block and tackle, but a pulley system is fine. Okay. What's that?
Is that an axle with a wheel?
Yeah, it's a wheel and axle. You see what's going on here? You've got a rope that's attached. This rope is wound around that small axle, and that's what the box is hanging from. This is mounted somewhere, let's say. Right? And then this large wheel out here, you're applying an effort force or an applied force by pulling on this large wheel. Okay? So like all these other machines, we'll talk about this soon. This has the ability to either multiply force or distance. And we'll get into more detail in a second. So we got levers, we got pulley systems, wheel and axle. What's this? Ramp. What's our technical term for that? It's a ramp. But what do we call it in physics?
A slope or
Incline.
Inclined plane. Inclined plane is what usually it's referred to. But it's a ramp. It's just a ramp. And then what about this? You may not have heard about that one. Now, this is one we talk about so much. It's a wedge. Yeah, it's a wedge. And then what's this? A screw. Yeah. So those, and what we're going to see here is that we've copied ourselves a bunch of times. Really, all this stuff, these two machines right here really describe all the rest of these. All the rest of these are just permutations of levers and inclined planes. Those are the two fundamental simple machines. Okay? So let's talk about these things then. So for all simple machines, and we'll look at each one of these in a little bit of detail. For all simple machines, there are some things we can say that are always going to be true. First of all, the ideal mechanical advantage, which is sometimes called the theoretical mechanical advantage, same thing. Ideal, what's the word ideal? In a perfect world, right? So that's also theoretical mechanical advantage, or TMA. They're used pretty much interchangeably. And then they call this mechanical advantage, but probably we should put an A in front of that. It's actual mechanical advantage. Okay? So what is the actual mechanical advantage? It's always going to be the ratio of the resistance force divided by the effort force, which is another way of saying that would be the output force divided by the input force. I much prefer using the words output and input. For a machine, what's the input force? Just in general terms. Well, it's at some level, but like with a lever, right? Here's this bottle opener, just a lever. We'll talk about that here in just a little bit. But where's the input force coming from?
Mechanical.
What's providing? You are. Yeah, you're inputting the force into the machine. It's always the force done by the person, right? Or whatever the agent that's causing the force is. For us, it's going to be people. So the force you apply is the input force. What's the output force?
Force on the object.
The force on the object, right? That's actually applied by the machine. You apply force to the machine applies an output force to something, right? So you're in, machine is out, okay? So it's always going to be the actual mechanical advantage is always the ratio of the output force divided by the input force. So if you have a mechanical advantage that's greater than an actual mechanical advantage, why might that be useful? Like what if you had an actual mechanical advantage of 5? What's that doing?
5 times the work you put in.
Yeah. That means the ratio of the output force to the input force is 5. In other words, the output force is 5 times bigger than the input force. That's obviously could be a huge advantage to us, right? People are relatively weak, compared to elephants, let's say, right? we need to be able to multiply using our brains. You got to be able to multiply our input force to move big objects, and so we can harness the mechanical advantage of a simple machine to do that for us, right? Can anybody think of a reason why you might want a mechanical advantage that's less than 1, like 1/5?
Usually increases the output speed.
So, okay, so it's increasing, so what that's doing then is, what we're going to find is that it's the force, work is force times distance, right? So in a perfectly efficient machine, the amount of input work is always going to equal the amount of output work. It doesn't sound like you're gaining anything. Okay, let's take an example where I'm just going to skip ahead for just a moment here, and we'll look at this idea of actual mechanical advantage. So if we've got a lever, there are 3 classes of levers. This is the most common one that we refer to in a diagram. This is a first-class lever, where we've got this lever, and it's pivoting around a fulcrum. So think teeter-totter, right? You're going to stack a load on one end of the teeter-totter, and you're going to apply an input force to the other side of the teeter-totter, right? So what's going to be the amount of work that's done? Let's do a little calculation here. So if I were to, for the sake of argument, let's say that the distance between the fulcrum and the input force is twice as large as the distance between the fulcrum and the output force, okay? Without going into lots of geometry, does it make sense that if I were to push this thing down by just a small amount, the load's going to move up, right? Okay, what's the ratio of the distances that each of those moves going to be? If this distance is twice as big as this distance, if I push this thing down 20 centimeters, how far up is the load going to move?
10.
It's going to move up 10, isn't it? Right? And we could show that pretty easily using geometry. One easy way to think about it would be, if I were to push this thing down, it's going to move along, it's going to move along a circular arc. Everybody agree? Right? And this one's going to move along a different circular arc, but the radius of this circle is twice as big as the radius of that circle, right? Does that make sense? So if I were to look about it, if I were to think about moving this through a really large distance, like one complete circle, the circumference of this circle would be twice as big as the circumference of that circle, wouldn't it? Because circumference equals 2 pi r. If I double the radius, I double the circumference, right? Well, we're not going to move it through a whole circumference. We're just going to move it through a certain fraction of a circumference. Maybe we're going to move it through 10 degrees, right? But if I move this through 10 degrees and this one moves through 10 degrees, they both move through the same fraction of one complete circumference, right? But this is twice as big a circumference as that one is. Okay, so I mean, we don't even really have to go into all that detail. It's pretty intuitively obvious to us that if the distance between the fulcrum and the input force is twice as big as the distance between the output force and the fulcrum, we're going to have to push twice as far to move this thing a certain distance. Okay, but what's the advantage of that? Yeah, the effort, right? Turns out that I only have to push half as hard here as the force provided at this end, right? So I only have to push with half of the force associated with the load. Now, what's the work done in both cases, though? Think about this. Let's think about the work here. We're going to have large distance, small force, right? So here's how I'll denote that. We'll think about this as the input work equals small force times large displacement, right? What about over here? The output force, or output work, sorry, is equal to a large force times a small displacement. Well, what's the net result of the two things? They're the same. The work in and the work out are the same if it's a perfectly efficient machine. In reality, with a lot of simple machines, you're actually going to lose some energy in the process of using the machine And the output work is probably going to be actually less than the input work. You're actually doing more work on the machine than the machine is outputting for your benefit. Okay, it still might be worth it though, because maybe you really need to multiply that force. That's the crucial thing. Maybe it's not a big deal to, to push this through a little bit larger angle. We don't care, no big deal. So I push it this far, push it that far instead of that far, big deal, right? But if I can magnify my force, that might be a really big deal, right? So if we think of this in terms of saving work, you're always going to be disappointed, because the very best you can do is get the same amount of output work, you get the same amount of work out as you put in. More likely, you're going to get actually less work out than you put in, but that's not what we're concerned about. We're just concerned about multiplying the force in most cases, okay? Now, I asked the other question, can you think of an example where having a small mechanical advantage less than 1 might be useful? Well, yeah, we could go back to the same picture, and let's say instead we're going to flip this thing around. So let's put the load over here on the right side, and we'll push on this side, okay? So now I'm going to apply, maybe I've got the ability to apply really large forces in this case, but I don't want to have to push this thing through a very large distance, right? Say I've got a very light object on this side, maybe a projectile on this side, right? And I'm going to push really hard on this side of the lever through a very small distance. But if I push this thing down pretty fast, if I cover a relatively small distance pretty fast, on the other side I'm going to cover twice as much distance in the same time. And so I multiply the distance and therefore the speed at which I'm moving the lever. Does that make sense? And so you've all probably done this. You put at the dinner table, you put a knife over a little fulcrum, and then you put a pea on one side, and you do that, and you shoot your sister in the head with the pea, right? So you're just using a lever to multiply the distance because you have an excess of force to spend, right? So sometimes it is to your advantage to actually have a mechanical advantage less than 1, okay? All right, so actual mechanical advantage is literally the ratio of the output to the input force. Okay? What's the ideal mechanical advantage? In a perfect world, theoretically, if there are no non-conservative forces acting, no friction, no energy losses, we can always predict what the mechanical advantage of a machine is going to be based on the geometry of the machine, right? We could have, for this last example, instead of measuring output forces, just by knowing that what we call the input arm or the effort arm, which is the distance from the fulcrum to the input force, knowing that that's twice as big as the output arm or the load arm, should predict for us that we're going to get a mechanical advantage of what? If I'm applying the force over here, so let me put some numbers up here. So if we're saying that this distance right here is 2 meters, and that distance is 1 meter, what should the mechanical advantage be? Should be 2, because I should only have to pull or push with half as much force. I should multiply my input force by 2, shouldn't I? In this setup right here. Everybody agree? Theoretically, that's what the mechanical advantage should be. What is it actually? Well, if we measure it with force meters, we might find that it is 2. With a lever, do you suppose there's going to be a lot of frictional effects here?
Not a lot.
Yeah, almost none. Almost none, because this thing is just, if it's a good quality lever that has a sharp fulcrum, there's going to be very, very little. I mean, it might be just a fraction of a percent.
Like 1.9999994 or something.
It's going to be really small. Yeah, it's going to be really, really small. So in this case, what we predict from our ideal mechanical advantage is going to be pretty closely matched by the actual mechanical advantage when I measure the forces, right? But that's not always the case. How could we describe how closely the actual mechanical advantage mirrors the ideal mechanical advantage? Efficiency, yeah. So the efficiency, we could say this in a number of different ways. One way to calculate efficiency is to just take the ratio of the actual mechanical advantage divided by the ideal mechanical advantage. And then if we want to write that as a percentage, of course, we'll multiply by 100, right? Okay. The other way we could do that, which ought to make intuitive sense here, is we could ask ourselves, well, how much of the input work are we getting back out as useful work, right? I'm gonna get the same number. If I input 100 joules of work and I only get back 90 joules of output work, that's only a 90% efficient machine, right? What's that mean? Well, it also means that my actual mechanical advantage was only 90% of what I thought it was gonna be ideally. Okay, that all make sense? Okay? So there's the you know, the basic gist of what we're going to do for all these machines. Now let's look at individual machines. Okay, so if we're going to look at lever, so let's define the anatomy of a lever. We already kind of did this, right? We've got effort force, the same as input force. That's what we're putting in. Output force is the same as the load, what we're trying to lift with the lever. We call that the load. Fulcrum goes in the middle for a first-class machine. And we say that we call the distance from the fulcrum to the two forces, the output and input forces, we call those arms. We've got the effort arm or the input arm and the load arm or the output arm, same thing, okay? So classic example of a first-class lever, which is where the fulcrum is in the middle, is a teeter-totter, right? So first-class lever means fulcrum goes in the center. You've got the input force on one side and the output force on the other side, and the fulcrum is in between. That's like a teeter-totter. What about a class 2? Okay, a class 2 lever is where the fulcrum goes at one side, it's at one end, and the load is between the fulcrum and the input force. Can you think of something like that in everyday life?
Would that kind of be like a crowbar?
I mean, you could use a crowbar that way, or a pry bar.
Yeah.
Can you see, like, what if I wanted to, let's say I had, this stuff, I think this stuff's kind of good. Like, what if I had to pick this desk up, right? It was really heavy. There was something I had to pick it up momentarily to move something out from underneath it. And I had a long 2x4 to do this. What could I do? Well, I could take a 2x4 and stick it under the table so the end of the 2x4 was right about there, right? And then I'm going to run the 2x4 up underneath, and if I pick up from this side and pivot it about that point on the ground, it'd make it a lot easier for me to pick that desk up, wouldn't it? Everybody agree? Second class lever, right? What's another one? If you do yard work, you probably use this a lot.
All those things that you weed with.
That's not what I was thinking of, but
A
maybe.
shovel?
Shovel, not so
No.
much a shovel.
Shovel would be more classical.
Wheelbarrow, yeah, wheelbarrow.
Oh,
Yeah. Right, there's your wheelbarrow. You're holding the handle, there's the tire, and you put all the dirt in the middle, right? Does that make sense? Okay. So, is this going to provide a second-class lever? Tell me, what can you tell me about the mechanical advantage? The second-class lever. There's a general statement you can make.
It's less, it's always not as much.
It's always something. Now think what
Yes.
think what ideal mechanical advantage is, right?
Mechanical.
It's always going to be, now notice it's opposite, the ratio is opposite of actual
It's always gonna be
mechanical
less than
advantage. Say it again?
It's always gonna be less than one.
Less than one?
Greater than.
Greater than one. Right, because actual mechanical advantage is the ratio of output force over input force, but ideal mechanical advantage is the ratio of input distance over output distance. Makes sense, right? Because you increase force at the expense of distance and vice versa, right? They have to move, they're inversely related, right? So if the output force is bigger than the input force, then that must mean that the input distance is bigger than the output distance, right? So if we wanted to calculate for a second-class lever, if we want to calculate the ideal mechanical advantage, well, look at the lengths of the arms here. So here's the input arm, or the effort arm, right? So we'll call that D sub I, input arm. Here's the output arm. Which one's bigger? The input arm is bigger, right? The input arm will always be bigger on a second-class lever because that's what a second-class lever is. The load is in the middle, right? So you're always going to get a mechanical advantage bigger than one with the second class lever. Okay? Then last example would be a third class lever. Okay, what's this do? Well, this time the fulcrum is still at one end, but we're flipping the output and the input, right? So this time we've got the input in the middle and the output is at the other end. So what's an example of that?
Why are there two triangles?
Okay, why are there two triangles there?
Because the input would just make it go down.
Right, so what this is saying is if we were to push, if I just put a triangle on the bottom, I mean, this is kind of, you don't really have to have them there, but it just looks better, because if I were to push up hard here with the input force, and the load were pretty heavy, and I weren't constraining this thing on the top, what would it do?
I just think we go that way.
Yeah, yeah, so all this is saying is it's gonna be, we're biting the other end of the lever between these two pieces, where it can move, it can pivot freely. So it's like an axle there or something, okay? What's an example of a third class lever?
Catapult.
Catapult, exactly, catapult. So think what a catapult does. With a catapult, like you wind up, you create all this elastic energy, right, by winding up this spring, and it's attached, you develop really high forces, right, because you can wind this thing up with a long lever. And it's applied relatively close to the pivot point. And then way out here, far away, you're going to put a relatively light projectile. And so as this thing springs and it moves through an arc, the speed is increased out here, and so you get these really high release velocities, so you can project something for long distances, right? What's an everyday example you think of? What do you think? I mean, it's a little harder to see this one, but even things like a tennis racket. A tennis racket would be, say it again? Door? Yeah, a door would be one, sure. Yeah, like with the door, if I open this door up right here, and I push right there, that's a third class lever, isn't it?
Is there a class where the effort is directly on the load?
Well, I mean, either one of those technically could be.
class two.
That would be the, you see what I'm saying? It would be the same thing. It would be,
2.5.
if the effort was right next to the load, what's really the advantage of that?
Not just indirect.
Yeah, you know what I mean? There really isn't an advantage to that. I mean, it's, both of these in the default in-between case, class 2 and class 3 would converge onto that one. But it's kind of it's not a very useful case, okay? Like, I can say like a tennis racket would be, right? If you're swinging a tennis racket, think what you're doing. You're pivoting at about a certain point, and you're gonna apply a force to twist that thing near the base of the handle, and then you've got this long lever that's gonna move faster to make contact with the ball, or a baseball bat. I mean, does that make sense? Yeah, so wherever you're trading force for speed, and the fulcrum is at one end, it's a class 3 lever. So a couple ways you can remember this. This is kind of cool. So FRE 1, 2, 3. If you can remember that, you can remember how all the classes are, right? Because what's that mean? Well, if you look at the depictions of the levers, whatever's in the middle, it's going to be, what's in the middle for a first class lever? The fulcrum. What's in the middle for a second class lever? The resistance, right? What's in the middle for a third class lever? The effort. So if you just remember that resistance is the same as output, and effort is the same as input, because effort's what your efforts are doing, right? Come on in. Oh, you were worried about, come on in,
Why are you leaving?
I interrupted. So FRE 1, 2, 3, and that'll remind you what's in the middle. And once you know what's in the middle, the other parts are interchangeable, right? You just need to know what's in the middle on the lever, okay? So some examples real quick. How about I'm going to say it, and you got to tell me what it is.
Apple.
Pineapple? Pineapple, I'm not sure that's any of them. Okay, what about pliers?
Class 1.
Pliers.
Class 1.
Survey says,
1.
well, it doesn't really say, but it's clearly class 1, isn't it?
That's a freeze.
Oh, it's on free still. Class 1, isn't it, right? The fulcrum's in the middle, so it's class 1. Okay. The pliers typically, are they going to give you a mechanical advantage greater or less than 1?
Greater.
Greater. Or they're not very useful, right? Pliers, you want to be able to apply a lot of force to something, to grip it. Okay. What about chopsticks? Think about chopsticks here.
Class 3. Class 3.
Class 2, no, 3.
Yeah. This is, yeah.
Hold up the number of fingers to tell me 1, 2, or 3. If you're holding up 1, be careful. Okay. Ooh. Survey says that's got to be class 3, doesn't it? Right? Because what's in the middle? Oh, it's frozen still. Right? Because what's in the middle? The effort. Right? The input. Right? FRE 1, 2, 3. So E goes with 3. And then finally, let's see if I can remember it this time. What about a nutcracker?
2. Wait, what kind of nutcracker?
Just like the kind where you
Okay.
what's that going to be?
Maybe class 2.
Yeah, it's class 2, isn't it? Right? Fulcrum's at one end.
Inputs
Inputs on the other end, and the middle is going to be the load or the
I got
output.
her right.
Good job, Lamont.
Okay? A couple more examples. Okay, this time I'm going to randomly call on somebody here.
Oh, come on.
But
Not the dice.
it's for a treat, so it's worth it. you know.
What?
What do we give
Yeah.
prizes?
We could do it 27 times.
Sorry, just don't call my name.
Okay. All right, so randomly, I'm going to roll a die here, and whatever the last digit is. Okay, so 1, 2, 3, 4, 5, 6. Okay, Rylan, stapler. Stapler.
What? You were gonna staple? Oh wait, no, that's.
Would your list be wasting the staple?
Yes.
So you have effort and then fulcrum. So 2 right now.
So,
It's on the end. 1.
so I would take 2 of them. I would take. What's your final guess?
1.
I'm not going with 1.
Okay, 2.
Okay. So now it goes to Walter.
Yeah,
Stapler.
it's 3.
3. Okay. I'll take 3. I'll take 3. I mean, it's because
It does
really,
kinda depend on where you
Yeah.
press on the stapler.
it depends on what kind of stapler.
Well, you might hold it in the middle, or you might be on the.
Yeah, because you could press. You
If
could.
you're on the end, the load's still.
You're still
No,
in
because the load is the
Can we
staple.
establish that this is not super competitive?
Yeah.
All right, thank you.
Yeah, the load is the staple.
There you go.
On the end. But you could.
Okay.
No, you couldn't, you still be in front of it.
No.
You know, this is gonna bake inside my car.
Okay.
You
Now
could still be-
the human bicep. The human bicep. So I don't want to scare you. I don't want to show you my big guns. But if you're picking something up like this,
Oh,
okay, I want to know what that is. So if I'm going to use my bicep to pick up a weight, think about that one.
Yeah.
Hey, Greg.
Did you get that email? Can you hand those out to your 7th period class?
7th period. Oh, I got you.
Yeah.
Okay, can do. Okay, can do. Bicep. Let's see. So this one goes to for Stanton.
Would it be a class 1?
I'm gonna say no on class 1. This one goes Cyrus. Class
Please excuse the
2.
interruption. Any students that are outdoor school counselors, there's a mandatory meeting tomorrow night at Sunridge.
Look
in
at
the
that.
choir room.
What do you think?
And if any students that are
That's a
in
tough one.
outdoor school
I think
counselors,
that was like a
there's
class
meeting
1.
tomorrow at 6 p.m. at Sunridge in the
Well, it's a
choir
fine
room.
before it's a
Okay. So it is class 3.
Email from Mrs. Demenew before
You
the
see
end
why?
of
The
September.
loading, or the load arm is your.
So there's the fulcrum.
Fulcrum is your elbow.
Here's the output.
Yeah.
The input force is gonna be in between. In fact, it's pretty close to the fulcrum, right?
Like say.
Muscles are
like
pretty strong.
Right around here. So,
Okay?
Whoa, we need our muscles to be attached up here.
Oh, that'd be really scary.
Kind of.
Nick, that'd be really scary.
Yeah.
Like,
Yeah.
rookie scary.
Wait, now it kind of makes, it make it